Now we finished our introduction to logarithms and exponential functions. Let's talk about two very special types of logarithms and exponential functions: the natural exponential function and the natural logarithm. So what is the natural exponent? E. If you look at your calculator, you'll see a button E. And what it is just a number. It's a number 2.718, and it goes on forever, and it doesn't have any combination that keeps repeating itself, right? And in that sense, it's a lot like pi. Pi is just a number. It's a very special number too. It also is a irrational number, so both of them are irrational numbers. They cannot be represented as a fraction, so there's no way to say that pi is equal to, something over something else. Can't do that. And E, similarly, there's no way to write it as a fraction like that. And so formally, they're both irrational numbers, and both of them are non-terminating, non-repeating decimals. They go on forever. So if you look at your calculator, you probably notice you've got two buttons, a pi and an E, and those are very special numbers. The natural exponential function is very useful for the social sciences, business, and economics. And it has the form e to the power x, or if we wanted to see something like, say, population was a, we could write it like that. Looking at the natural exponential function on a graph, you can see that if x is equal to 0, both of them are equal to 1. And they are, we've got e to the power of x and e to the power of negative x, and they're mirror images of each other around the y-axis. So you probably know that pi is special because it helps us look at the circumference of circles and the area of circles. So what is it that makes the natural exponent e special? Why is it so special and so important that it's a button on your calculator? Well, it turns out that E is the solution to a number of mathematical problems. And so it solves more than one problem. And so mathematicians find it very curious that this strange number has a sort of a bunch of different uses. Now, I won't give you the problems that it solves at this point because you don't need to know it. As a student of business and economics, you are going to find it very useful. And one property that makes it very useful to you is that it captures continuous growth. And I'll demonstrate this with an example. Here's our Canadian population question again. This time, we're going to look at it modeling or using a function for continuous growth. So before, we had something like, the population in 2100 was equal to 38 times 1.014 to the power of 80. And the problem with this is that if I sort of graphed it the way it's being calculated, t here, the Canadian population, and let me put a 1 here, 0 here. The Canadian population is 38 million, and then it jumps. And it jumps to 38.5 million after 1 year. So we want, so this is non-continuous growth. If we want continuous growth, so suppose we want the population in Canada at the end of 2021, we can take 38 million, multiply it by e to the power of 0.14, right, per year, 1 year in the future. And we get 38.54 million. Now, the natural exponent is kind of special. So suppose I want to know what the population is in Canada in 1 month. Now, I told you it's continuous growth. And so if we drew a graph using the natural exponent function, and we had 1 here and t here, we had 38 here, and we had 38.5 here, and we would see that the population is going to grow smoothly over that time. Because of course, every day in Canada, people are being born, people are dying, people are emigrating, people are immigrating, and that's causing the population to change every day, or every hour of every day, every minute of every day. Maybe even down to the second. Of course, some seconds might change, might be 0, but that's the idea of continuous growth. You can break it down to a small amount of time as you want, an infinitesimally small amount of time. So to demonstrate that to you, let's look at the second question. So in 1 month, how many Canadians are there? Well, I can change this. Let's say that 1 month from now is 2020 February. So we're pretending that it's January 1st, 2020. That population is going to be equal to 38 e to the 0.14 times 1 over 12. Let me rewrite that and make sure that it's clear. Times 1 over 12. And the answer is going to be 38 million and 44,000 people. So that's kind of neat. That's something we can do with the natural exponent, the natural exponential function, that we couldn't do as easily with the function I showed you before, our regular exponential function, where we had the growth rate to the power of the number of time periods. The natural exponent is just another exponential. And so if we have e to the x times e to the y, that's just equal to ex plus y. If we have e to the x divided by ey, that's just going to be equal e to the x minus y. And if we have e to the x raised to the power of y, that's going to be equal to eyx. So same exponent rules that you've seen before. Here's an example for you. Press pause on the video, try it yourself, and see if you can get to the right answer. All right, if you've given it a try, let's walk through it together. We've got Japan as the case study. Japan's birth rate is 0.73% and its annual death rate is 1.02%, and both of them are continuous. So since they're continuous, we're going to want to use the natural exponent. Now, what's the growth rate that we want to use? Well, the growth rate of the population per year is going to be 0.73% minus 1.02%. And we have negative 0.29%. And so that's going to be how this population evolves over time. And we're going to use this constant growth rate. Now we're going to put it into our exponential function. So we have the population in 80 years is going to be equal to 126 million times E. Remember, we want to put this in as a rate. So we've got negative, so we can have exponential growth, or we can have exponential decay. Negative 0.0029 times 80. Plugging this into my calculator, I end up with 126 times 0.793 approximately. And the answer is 99.9 million. Here's a tricky question. Read it yourself, give it a try. If you can't solve it, or if you think you have the answer, press play and we'll go through it together. Now we're looking at a population of black squirrels, and we're going to assume that they're growing at a continuous rate. Which is nice. We can use the natural exponent. We're not going to worry about seasons. Now we know what the population of squirrels is 2.5 years ago. It was 200 members. 14 months ago, a group of 30 squirrels joined the population from nearby. All the squirrels' population, whether they were the newcomers or the oldcomers, grew at a continuous rate of 36%. How many black squirrels are in this population today? Round your answer to the nearest integer, because of course we can't have a fraction of a squirrel. Now, we've got something happening 14 months ago and something happening 2.5 years ago. So why don't we convert everything into months? And so this is, of course, 14 months. And if we have an annual continuous growth rate of 36% per year, then that's like having a continuous growth rate of 3% per month. Now I'm going to use a little trick from finance, and I'm going to draw a timeline. And so we can think of the original 200 squirrels. This is t, well, I guess we'll call it minus 30, t minus 30. And here's today. The squirrels are going to grow at a continuous rate of E. We've already got our 0.03%. And how many months? 30 months. And so the 200 squirrels, how many of them? How many squirrels are we going to have from that 200 today? Well, according to my calculator, we're going to have 491.9, so we'll call that 492 squirrels. Now, looking back on the timeline, what happened 14 months ago? T minus 14, we're going to have 30 squirrels join the group, and those 30 are going to grow at 3% per month, and they're going to do that for 14 months. And so those 30 will become, well, my calculator says 45.66, so I'll just call that 46 squirrels. How many squirrels do we have in total? Well, 492 plus 46, we have 538 black squirrels. So I chose an example with black squirrels because they're cute. Well, I think they're cute. Some people think they look like rats with long fluffy tails. That That's why I picked the black squirrels. But you can see if we're interested in the growth of something else, perhaps like a dividend-paying stock, we could have a very simple, similar example